So without further ado, let's do that. Now the how much that rotation is going to be in some kind of angle. So a certain amount of degrees per unit as we move up this thing. So I'll say angle is going to be some angle amount that we type in. And then we'll say how high up are we right now? So our current position in the y-axis. So p dot y divided by some amount of height. So I'll walk through what I mean by all that. So let's say we started with 20 degrees per unit. And we'll say how high is it? Well, we're going to say when p is 0, when p dot y is 0, oopsies, we're on the bottom, and we know that this thing is 28 units tall. So height should be 28, because that's what we want to do. We want to normalize where we are in this. So this component, the current height divided by 28, will give us a value from 0 to 1, depending on what slice in the y direction we are in this thing. And that will be multiplied by the maximum twist, I should say. So not angle per unit, but really the angle overall. So when we're down here, 0 times 20 means rotate 0 degrees. When we're all the way up here, 1 times angle means we'll look in a rotation of 20 degrees around by the time we get up there. Now, that hasn't happened yet. We only just have an angle amount. So now we need to use that angle amount to actually build that rotation up. So let's keep going. We're going to build a rotation matrix. We talk about this a lot in Rigid's series. You can go check out Rigid's 1, which is free, if you want a more in-depth explanation of how transformation matrices work. But if you don't want to, suffice to say, it's going to be a 3x3 matrix, which is simply a instruction or a tool to multiply by some vector, to say rotate this thing. In our case, we're going to rotate our current position by some rotation to find the original, to find where we're sourcing from. The rotation itself is going to be around some axis. So forgive me if this is all very complicated, but this is volume 6, so it's going to get a little dicey up here. So I have CHV, channel vector. So some axis. So click this again. We know this is the one thing that will probably be the most intuitive. The axis is 0, 1, 0. We're rotating around the y-axis. You know, it's the one that goes up the middle of this thing. So okay, that makes enough sense. We're going to need that axis when we are creating our rotation matrix. Speaking of rotation matrices, here it is. So we'll say matrix 3, the 3x3 matrix, which is how we do rotations oftentimes in computer graphics. You don't need, the beauty of this is that you don't need to understand the actual nuts and bolts of the math. You just need to say, I know that I can do rotations with three-dimensional matrices, or with, not three-dimensional, but with 3x3 matrices. So trust in that at least. So I'm going to initialize this matrix to the identity matrix. What that means is it's like multiplying a number times 1. If I multiply 10 times 1, it's still 10. So anything that I multiply by the identity matrix is going to be the same thing. So I said earlier that what we're trying to do is we're going to take our current position and rotate that position around the axis. So for every voxel, rotate it around the axis to somewhere else. Currently, if we rotate it by the identity, nothing will happen. Not yet. So let's say, let's change our rotation matrix to actually be the rotation that we want. We can use the vex command, or function rather, rotate. We take as input a matrix that we want to rotate, and we'll say we're going to rotate it a certain amount, which is the angle, which we figured out before, and we're going to rotate it around this axis. So as you can imagine, we have everything we need. If we're doing a rotation, we're rotating it around a hinge. So here's the hinge that we're rotating around, how much we're rotating it around, and the thing that is being rotated, which itself is already technically a rotation, just has no rotation yet, but now it does. Now we've said, take this blank slate, rotate it some amount around an axis. So now it's stored. We don't need to say rotation equals this. It takes it as input and changes it in place. So we've done it. That's all the complicated math. In fact, that's probably the most complicated math of the entire lesson. And it's not even math that you really need to understand. You only need to understand it abstractly, which is to say, we now have a rotation stored in this. Now all that's left is to do it. So the place that we want to look up, the old location that we were looking up, the source, I should say, I'll call it original point, is our current position rotated. That's it. So instead of doing this density equals our current location, let's use the location we just figured out. And brace yourself. We've done it. Now, this is extremely rotated, so perhaps we went overboard with that. So let's maybe build it up from 0. Then you can see, look at that. Isn't that crazy? And look how fast it is, too. So I'm going to go into our camera. But this is what we want. So now when I scrub, you can see we've done it. So it looks like a kind of a tornado. Pretty cool. I'll save that. So I'm going to run a little flipbook here, and we'll see what it looks like. Oh, actually, before we let that run, let's go into the high quality lighting mode, just in case you weren't there already. But okay, good. Okay, so that didn't take very long at all. So we can see it's working. I would say that just aesthetically, I would like it to be a little bit chunkier than this. So I'm going to go back to our frequency stuff here. So we have 1.51 right now. Let's have all of these. So now you can see we have bigger features. You know, if I go look at this, it's just bigger and chunkier now because the frequency is lower. So that's pretty much it. Let's run that and see what we got. I can see some little like artifacting in our viewport here. I don't think that's going to be an issue actually in the rendering. I guess we'll find out in a minute. Probably not though. But let me do another flipbook of this now.